welcome to my presentation. I would like to start with a few words about myself. So my name is Kristof Holste. I'm working at the University of Gießen in Germany. Well, I'm 44 years old, so I'm not young anymore, but even not old, so I'm somewhere in the middle. I'm an atomic physicist by training, and I'm working in the field of electric propulsion since, I would say, about 12 years. I would like to talk about plasma physics and what we are doing at university level to contribute to such a project. First, a few words about what is a plasma. We know 4 states of matter that are relevant in our life. So we know what is a solid, we know what is a liquid, we know what it is a gas. And there is another state of matter that we call plasma. And in a plasma, we can imagine that as a very hot gas. And the gas is so hot that we don't just have neutral particles, but we also have electrically charged particles. So electrons can leave the atom, and we have a mixture of neutrals, of ions, and of electrons. And this is what we call a plasma, more or less in a simple way. And well, plasma seems to be something, well, quite exotic somehow. But if we look in the universe, we see that almost everything visible is in a plasma state. So 99% of visible matter is in the plasma state. And it's important to emphasize the word visible here, because there's also a lot of invisible matter, what we call dark matter or dark energy, which we don't see and where we don't have any information about. But this is another topic. So everything more or less that we see is in a plasma state, and the very famous pictures one can get if one, let's say, Google that, are these, let's say, nebulas in space. So a nebula is nothing else than a region of, well, interstellar ionized atoms. Mostly it's hydrogen, and they emit light. And well, in our solar system, we have the sun in the center, and the sun is nothing else as a hot plasma ball that is heated by nuclear fusion processes. So how is a plasma correlated with electric propulsion? So if we look at, well, I have one equation on my slide, and it's the only one. But on that you can see something. It's the equation here. The thrust is given just by 2 very simple things. It's given by the exhausted mass per time that leaves your rocket, your thruster, and there is the exhaust velocity. And the exhaust velocity can be very high for an ion thruster, for an electric propulsion thruster. Because if we use ions, charged particles, we can accelerate them with electric fields to very high velocities. And if we do that in that way, we need less mass that we consume for a given, let's say, time unit. That means space propulsion with ion thrusters is very mass efficient. And that's the reason why we do that. We are, let's say, a factor of 10 more efficient. That means we don't need 1 ton of propellant. We just need 100 kilograms on our rocket, which is a big difference. Disadvantage here is that our thrusts are lower, but if you are in space, you don't need that big, let's say, thrusts, this mega Newton thrust that you need to start from Earth, yeah, for launch. So in space, it's very, very mass efficient to use ion thrusters. And well, the electric propulsion enables new types of space missions that wouldn't be possible, not possible, or even not possible so easily to do that with chemical rockets. And there are 2 famous missions. An older mission was GOCHE, Gravity Field and Steady State Ocean Circulation Explorer, was from 2009 to 2013. And this was a mission that performed a detailed measurement of the Earth's gravity field by using a highly sensitive gradiometer. And this was a very successful mission. And you see here on the left, there's an ion thruster. And Goce was flying not so high, maybe only 300-400 kilometers, and there was still some residual gas there, that causes some drag on that spaceship. That means you have to compensate these small forces that slow down your satellite, and this was performed by an ion thruster, running more or less permanently for a few years. And was already mentioned, at the moment there's the Spepi-Colombo mission, a satellite shown here in an artist illustration, where we have only electric rockets, only ion thrusters that are used to travel from Earth to Mercury. I think the travel takes about, I'm not sure, about 9 years maybe, and so the mission started in 2018, and the end is foreseen in 2027, 28, and so on. So Goce was, I think, was an ESA mission, and this Spepi-Colombo is an ESA, a joint mission between ESA and the Japanese space agency. Well, EP, electric propulsion, is somehow a game changer because it's mass efficient to use EP in space, and the number of satellites is increasing over time. This is 1985, there were 10 satellites using EP in space, and 2018 we had already 257, and nowadays there are these hundreds of satellites from these big constellation systems, Starlink from SpaceX, and there is, I think, Kuiper from Amazon, and OneWeb, and so on. So there are hundreds and thousands of satellites, and all of them use electric propulsion to propel, to move the satellite in space. In Gießen, we mainly focus our research on one type of these thrusters. So this is something that is common standard, I would say. So mostly a university is specialized in one or two types of these thrusters. Of course, they are somehow a complex thing. And the radio frequency ion thruster that we investigate in Gießen is shown here as a schematic drawing, or as a 3D CAD file. What we have here, we have a discharge vessel. That means a chamber where we inject the gas, and this gas, this propellant gas, gets ionized somehow. So we ionize this gas, we ignite our plasma, and in the second step, we accelerate ions, or we pull out ions from our plasma by using something that we call extraction grid system. This is shown here. That means we accelerate with electric fields our ions, we produce our thrust, and if we just shoot positively charged ions out of our thruster, we have to somehow neutralize our beam, otherwise we would charge our satellite, which we don't want. So if we would like to operate such a thruster efficiently, we have to learn a lot of things about our plasma, because the plasma properties mainly determine our behavior of our thruster. So we have to learn everything about the thruster, and there are a lot of ways how we can do that. This is a typical research project. This is the plasma diagnostics. A very simple way to do that is just to look on the light that gets emitted by our thruster. So you see here, this is our discharge. This is not really a thruster, but it's something similar, a way how we produce the plasma in a thruster. But here we use this setup to make optical emission spectroscopy. This is this was done in a PhD project, and the let's say what one has to do is to correlate such an optical emission spectrum with a model that you have to develop to, well, predict the measured spectrum with something that you put into your model, and if the model is right, you get the same result. That means you compare experiment and modeling efforts to say something about your plasma. And the trick here is to, well, you have atoms and ions, and they all have these energy levels, and they get occupied. Electrons can occupy different levels. They excite, they de-excite, they emit light. And this has to somehow to be correlated. So this is a typical research project one can do in a university environment. Another thing, what we do in Gießen is we are looking for alternative propellants. Most of the ion thrusters nowadays, they are using xenon as propellant. Xenon is expensive. It's a rare gas. It's expensive, and there isn't enough xenon for all of these thousands of satellites. So SpaceX is using krypton to work on their satellites, on their Starlink satellites. But even krypton there isn't so many krypton, I think, that thousands of satellites can operate maybe. So we are looking for alternatives, and one thing we are investigating is we're looking for molecules. That means we study molecules, how they behave in a plasma, how they behave if they collide with particles of a plasma, such as electrons. And we are looking, well, molecules can dissociate or fragmentate, and we are looking for these processes and want to understand if this is a problem or not, if we will use that as propellant for thruster. And even for, let's say, for students, we have a typical project is the development of diagnostics. Shown here on the left is our facility, one of our facilities, where we have a thruster here in the middle. And there are these things that let's say, these things can move in front of our thruster, and they measure something. They measure maybe the ion beam, they measure ion energies, and whatever. And typical student projects shown on the right is to develop some type of diagnostics, some scanning device that get information about your beam, and this correlation can be correlated to our plasma again. This below on the right side, this is some so-called pitot tube that measures how many neutral particles coming out of our thruster. So we have to somehow to get rid of the ions and measure the neutral density, the neutral flux. So this is a typical student project here at Gießen University. Well, we are doing experiments all over the world. We compare facilities because different facilities behave different. And you see here on the left, we have two of our students. They are just preparing some kind of measurement. On the right, looks similar, but it's another vacuum facility, test facility at Georgia Tech in the United States, where one of our PhD students is also preparing some experiment. And well, my last slide is this one. I have to say, working in such an in such a field is an international thing. So these projects, these European Union projects, for instance, they are we have partners all over Europe, and as a university we have partners all over the world. And this the space sector is a supranational thing. And well, with that, I would like to thank you for your attention, and if there are questions, I'm looking forward to answer them.